Our next speaker is a dear friend of mine, Jean-Baptiste, will talk to us about dav1d, an AV1 decoder.
Hello, do you hear me? Yeah. Okay, I wonder why half of the room is here, because you know probably better than David than me, but let's try anyway. Yeah, oops. Okay, so, yeah, that doesn't work. Yeah, I'm using Kelly with Wayland and sometimes Crashy with LibreOffice. Yes? No, that doesn't. Why does the clicker not work?
Yeah, it works.
Okay, so I'm the president of Videolan. I work on various open source projects, including VLC, 264, dav1d, FMPEG, and others, where I maintain some DVD stack and a bit of Blu-ray stacks. I'm annoying to many of those projects when they screw up. So I'm not probably the biggest developer there, but I'm doing everything else. No? Yes? So, AV1. So VP9, is AV1 just VP9++? VP9 is a semi-failure. It's a good codec, but no one uses it. When you ask YouTube, they don't even have many people actually submitting video in VP9. And there are many reasons for that. The reason is mostly because there was no spec for a long time. There was a codec, but no specs. There was absolutely no ecosystem except a few open source tools. Have you ever watched an anime in VP9? Maybe, right? One? Okay, amazing. You're the only one, right? But you've never been on the Pirate Bay, right? And so a VP9 encoding anime, right? So the format is a failure. One of the reasons also is that H.264 was so good and so well integrated that it worked. So they decided, so except YouTube and Netflix, no one actually used VP9 largely. So for AV1, they decided to not just do VP10, but to do something that it was actually open with an actual ecosystem. And I think that more or less they managed to do it. It's interesting that basically there is 3 companies that actually worked on AV1, Mozilla and Cisco plus Google. And there is an actual alliance for open media, which is open, and where people actually contribute. Well, we cannot say that about VP9. So AV1 has a lot of amazing results. We're talking of 20 to 25% better than VP9, and around the same around HEVC. And you can discuss about so many cases. But that's the rough numbers that you should remember. 20% better than HEVC is a good number, 25. And there is a lot of things happening on the ecosystem. There is at least 3 open source encoders. One is going to be presented just after my talk. There is a libom encoder, which is the reference one, which is extremely slow and a difficult code base. There is a new one that is happening that's called SVT AV1, which is basically done by Intel. It's difficult to talk about that because 6 months ago it was nowhere. They were announced it at IBC 6 months ago, and they're advancing fast. It's actually usable to produce some videos. But a lot of non-open source people are working on AV1. There is Eve, that is a very good encoder about AV1, extremely slow also. Atem, Harmonic, Bitmovin also are doing a lot of things around AV1. And there are actual hardware encoders like NG Codec is working on, and some other mostly Chinese companies working on FPGAs or ASICs for AV1. There are actual deployments of AV1, almost since day one. YouTube, Netflix, Facebook, but quite a few cloud vendors who are selling a lot of things about encoding video have an option to encode to AV1. So people care. And you know what? There are specs, and there are even specs to put that inside MP4, MKV, TS, and other stuff like that. Amazing, right? And this year is the year of AV1 because hardware is coming. Intel has more or less announced that they were doing it this year with their Gen 10 chips. NVIDIA has also more or less said that they were for the next chip, so probably around when they announce product, which is GDC usually. AMD also, but the Samsung TV at CES had AV1 decoding. Logic, Broadcom, and a few others I forgot show chips that were actually usable, produced that can decode AV1. And all of those can decode both 8-bit and 10-bit, which is quite important because you remember for H.264, lots of people just had 8-bit decoders and not 10-bit. And 2020 is also the year of the competition. Like you probably heard about VVC, which is coming in July, EVC, which is coming between April and July, which is basically a version of a VVC with less patents. There is something called MPEG-5 LC EVC, ECV, something like that, which is actually not a codec, but just like post and pre filters. And the AOM community is already talking about research on AV2. So things are going fast. So is that an actual competition? I don't think so. VVC is amazing in terms of technical quality. Most of the improvements are based on HEVC, and HEVC have 3 or 4 patent pools, so like you can expect that since H.264 had 2, VVC is going to have 5 or 6 or 7. Means like no one can actually deploy that because it's insane, those many patent pools. And there is so many people who are now big companies who are just turned into patent holes like Nokia, who are outside of patent pools anyway. And so the question is, are improvements good enough to justify the cost? Well, like HEVC is not deployed anywhere than broadcast, so everything that is online is basically skip that. So I guess it's going to be the same for VVC. EVC, which is like, oh, we're not really so much patented, but then you remove some of the gain. So like if you remove so many of the gain, you're going to be at the level of AV1, then why not choose AV1, right? And then like other stuff are actually not codecs and could be applied to open source codecs. So I think that even if competition is coming, they're going to have, that's their last big shot, and they might have like difficulties. So David. David is an AV1 decoder, as the name says. The idea was that we actually need to have a good and fast software decoder, because like a lot of people are not going to have hardware decoders, and until people can decode, then you're screwed because your codec is not being played anywhere. And the problem is that everything you're going to see, it's true for AV1, for VVC, and all the new codecs, they are very complex. Like a lot of code is required to write an AV1 decoder, because like we tried to take any small gains. So there is lots of tools, and you take 1% here, 1% here, 1% here, but that's a huge code base compared to H.264 or VP8 or VP9. So the idea was like, we need to have a very good software implementation that is extremely fast, and like every cycle counts, because if we are going to deploy that, it's going to be billions of people who will still have their correct and actual machine that they have today and not their new machines. And if we don't have that, then everyone will fail. The idea was to use basically the people from VLC, FFmpeg, and H.264 who actually know how to write C and know how to correctly write portable and cross-platform tools, and don't use CMake or some weird configure stuff like libvpx and libaom that basically is impossible to port to so many platforms. And one of the goals was to have a small binary size, because for YouTube or Facebook, when they ship the decoder in their Android apps, they actually care about the binary size. And that was, for example, the mistake that was done in FFVP9, which was a FFmpeg VP9 decoder that was done before by basically the team that basically did David. And they didn't care that much about the binary size, and that was an issue. So we launched it, well, last year, now almost 1.5 years ago, in October 2018, and we had like a release quite soon after, and it's been improving quite a bit. Just a bit of history, like announced was in October, like already like 3 months after we had like the first release, which was already 4 times faster than the reference and the only decoder at that time. And that was, of course, focused on x86, 64 bits. And then, like, after 3 months, we did another release, which was focused on ARM. Like, we are already twice as fast as libaom on ARM 64. And the same, we went, every release, we focus on, like, less important platforms, like ARM32, and then SSE3, and then even FFC2, and so on, and so on, and so on. So we have, like, one release every 2 or 3 months, which is quite nice. Performance is amazing, right? Like, we're talking about 3 to 5 times faster than the reference decoder. The reference decoder has assembly in it, right? Like, it's not like we're comparing C to non-C versions, right? It's assembly against assembly. When we started, Ronald, who wrote a lot of the code of David, said, yeah, we might be 2 or 2.5 times faster. No, we're a lot faster. And we're even faster on SSC2, where we did not write as much assembly as we did for the other platforms. Then ARM. So ARM, you can see that I'm comparing to the new, oh yeah, wow, I got a LED. The new one, which is libg AV1, which is another decoder wrote by Chrome, and totally not in a non-invented year syndrome fashion, because they really wanted to have one that will be faster than David on ARM. So that's the blue one. And as you can see, well, David is quite a bit faster already. And they're improving, but they're not getting close to us. So we're talking 2.5 to 4 times faster than the other decoders. That's a question that was asked quite a bit in the past, which was, what is the complexity of doing AV1 decoding? So here you can see in yellow, which is the FF8264 decoder, so the decoder of H264 inside FFmpeg. Then you have in red the VP91, and then in green you got HEVC and David. What you can see more or less is that, of course, VP9 and H264 are way easier to decode, but that when you spend enough time on David, on AV1, you can do decoders that are around the same complexities than HEVC. Then you're going to say, yeah, but you didn't spend enough time in HEVC. Sure, we could maybe make the HEVC decoder a bit faster, but not so much faster. So AV1 is not that complex to decode in terms of CPU, but as there are many tools, it's long to code. Okay, are there some weird stuff on the David? Yes, there are two. Oops. There are two things that are weird for a decoder. The first one is that it's a dual pass decoder, not encoder. You see, I just made a mistake. It's quite rare to have that. The first pass is basically to analyze a few things, to be able to schedule after, and also to do a lot of parsing, because there is lots of things to parse at the entry point of an AV1 stream, OBU and other stuff that were probably not the best designed ever, but they were in a rush. And the second one decodes. And we have what is more important for most of the people is that we have a dual threading model. So we have a frame threading model, so you start decoding one frame before the next one. But at the same time, so we have a slice or tile threading models where you can basically, because most of the video you're going to see in AV1 are encoded in slice or tiles. So you can start decoding like the first row, the second row, the third row, and so on. So when you try to get the best performance out of David, you need to basically set both how many styling thread and how many framing threads you're going to have. And the thing is, we might add more threads for the filters. So we need to do something about that to have everything automatic and works at the best. And we would like not to use machine learning to decide that, even though it's completely in fashion to do that. The rest looks like a normal decoder like you have in libAV codec, except a bit bigger. So the question is, why is David faster than the competition? And there are three main reasons. The first one is here we're seeing the single thread C version, and you see that the C is quite well optimized and well written, because already the C version in single thread is fast. And more is coming, because there is one big part of David that is not optimized in the C version that is coming soon. In 2 weeks? Yeah, sure. In 2 weeks. The threading is quite amazing. So is this the number of threads? Yes, this is 2,000 threads. That is a graph that was done by some of the Mozilla teams. And you see that basically David actually scaled with threading quite a bit. And if you see libAOM or EJV1, they just cap around 4 or 8 threads, and then they don't improve, while David can still improve, which means that it's actually good. Oops, of course, the other way. And we write actually low level code. That means C. So libjv1 is in C++, so there is no C++ overhead. We write handwritten assembly, not intrinsics. Yeah, but intrinsics are easier. Yes, they are easier, but you lose between 10 to 15%. That's what we've seen lately on the various threads on the FFmpeg mailing list. Intrinsics are slower, almost always. So no interesting handwritten assembly. So basically, David is like, the C version is faster in single thread. We can scale better with threads, and we write lower level code, which means that, of course, no one is going to beat David ever. So basically, in an AV1, in David, there is like 8 stages that are basically that we managed to ISM correctly. The first one is the MSAC, which is basically an entropy decoder. There is inverse transform, the motion compensation, the intra-prediction, and then the full after is our filters. Loop filter, loop restoration, the famous CDEF, and the film grain. Film grain is quite debatable because lots of people don't like that. But so when you now start and run David and you perf it, you realize that the parts that are basically non-ISM are around 25% of the runtime, and that's mostly on the what we call the FMV and the decode coefficient. So that's for AVX2, FSC3, ARM34, and ARM64, ARM32. You can see that basically the optimization done for AVX2 are full, and there is not much to gain on writing better optimizations. There is just like a few tools, like in 444 or some intra-prediction that are not done. For SSC3 is probably one of the most difficult assembly to write because we need to support both 32 bits, which has absolutely no registers, and 64 bits, and you need to care about the Windows calling convention and the Linux calling convention, and of course Mac, which is another mess. So that's quite a bit difficult, but that was mostly done. There is some filigrane that is done, but it's not merged yet, so next release it's merged. And as you can see, we did some parts in SSC2 because that was easier. Mostly it's an entropy decoder, which there is no in AVX2. Some of the motion compensation, one of the loop restoration, and the CDEF. ARM64, you can see that mostly everything is done except the film grain. And ARM32 has still quite a bit of work to be done. The entropy coding, the inverse transform, which is large to write in for AV1 because it's quite large. And the intra-predictions, like there is DC, H, and V that are done, but the rest are not. Which brings me to that. Here you can see basically you can see so X264 is an encoder, it's extremely fast, it's blah, blah, blah. We wrote a lot of assembly. And when you look at the graph of X264, you see that around 25% of the code base is assembly, and the rest is C. And of course, like if you look, X264 is 68,000 lines of code, and around, you see 37 lines of code of assembly. And when you take the whole libAV codec, which is 500,000 lines of code in C, you see that it's 80,000 lines of code of assembly. But David is weird. It's only 25,000 lines of C, but it's already 64 kilo lines of code of assembly. That's like that's a lot more than X264, and almost as much as what you have in libAV codec, because there is the 10-bit ARM assembly and x86 assembly that is coming soon, and it's going to make that just for one decoder to be write more assembly than the whole libAV codec. We worked on something weird last summer. So if you listen to me like 1 year ago, I would say like, yeah, everything related to GPU is idiotic, it's too slow, there is too much latency. I've said that quite a few times. And other people of the community said that too, right? It's very difficult because then you have like the latency to upload the textures and get it back, and like it's quite difficult. A lot of tools are CUDA based, and which is like not open source at all, because like NVIDIA doesn't like open source. But we said like, what about we try anyway? In David, the film grain is already a GLSL shader, right? You have a C version that is optimized, but what we advise people is to actually do that in the player, because the film grain is really after your decoding is done. But the question was, can we do more? Can we do CDEF, loop restoration, and other loop filters? And it's very difficult because you cannot really know if it's going to be faster, but do you actually care about being faster or do you not? What you mostly care about is the consumption, right? How much battery drain is it going to be on your phone, on your Android phone? And because as soon as you got 60 FPS, you don't care of doing 70 FPS. It's only for gamers who care about 140 Hz. But for video, you don't care about that. What you care is to not drain your battery when you're watching your video on Instagram or in Snapchat or whatever you're watching. So we had a GSOC who did that during the summer. The guy had no idea about mostly AV1. And so he did basically the CDEF and the loop restoration, so both SGR and Viner in Vulkan shaders, tested on an Android Huawei phone, I think. Yeah, Huawei P20. And what you see is that, what we saw is that, like, we didn't get any speed increase. However, for like basically the same decoding time, so we put basically a VLC running and playing the file on loop, you see that basically we get 20% less battery drain on that, just by using GPU compute shaders, which was not expected. So what is the future? The next work on David is going to be, of course, 10 bits, and then decide what we can do about GPU, and how can we move that to the next level. Thank you, and I'm taking questions. Am I allowed?
Yeah, sure.
How much time do we have?
We have a lot of questions. We have a lot of questions. I'm not sure we'll be able to answer all of them, but let's start how the dual path requirements fits with the current low latency trend in the streaming world.
I don't think it matters much on the way it's done. It could be problematic in some cases, but I don't think it matters the way it's implemented. Maybe you should thread that also, but that should be okay. Are the Sysvel patent pool for AV1 valid? I would say no. There are surely AV1 patent pool patents that exist, because like there is a patent on absolutely everything. I think it's like very, very, very small things, so they don't matter at all. And I think it's just the usual FUD bullshit that they're doing.
All of this is for 8 bits, which is nice and fast. What about 10 bits and HDR?
Yeah, it's coming. Probably first will be ARM64 and then x86.
Is it possible to use AV1 as an intra-codec?
Yes. Is it a good idea? I'm not sure.
Why not?
I think there's stuff like FFV1 are easier to do that. I mean, like, I don't think AV1 was done for that, but like there are people around there that might know better. AVIF. Yeah, AVIF for images, but.
What are the major companies missing from AOM and to push VVC?
I would say that some of the people who are in AOM, like Samsung and Apple, are important, and we don't know exactly what they're doing because those are big companies.
Who is currently using David?
Oh, that's a good question. So every version of Chrome, every version of Firefox that is shipped, every version of VLC, FFmpeg, and most players based on FFmpeg use David. So that's around everyone that is shipping AV1 except Android.
What kind of operations do you use from SSC 3 that are not in SSC 2? Just technically.
Ask that guy.
There is a fewer, but PHD allows you to shuffle bytes in a vector register, and you use a mask of index to do that. And when you have to do that dynamically using relations that you can complicate it, so you have to write relations that are specific for each case.
Well, if you want more details, ask him. Can David use GPU acceleration? I think you answered that.
Yeah, no, that's not OpenCL, not CUDA. This is compute shaders. We're using Vulkan compute shaders and not.
When do you think we can expect wide AV1 support in cheap, low-end devices?
End of the year. September, you will have cheap or cheapest Android, like $200 to $300 devices that can decode AV1, 8-bit, 10-bit, 1080p. Real time.
Thank you, David.
Thanks.